So I'm going to discuss first what happens to the story yesterday if I were to break the flavor permutation symmetry that I had assumed. Now, in reality, I'm actually not going to do a calculation. I'm just going to tell you what the results are and sort of motivate why the results should be what they are. And in principle, to get the results, what one should do is to look at a discrete space-time lattice and then do the corresponding calculation that I won't do here. So before I jump into the details of that, there are two things I should clarify, which I didn't in the last two talks. So number one is that I was looking at Wilson loop order parameters around vortex-like excitations. In that case, I was taking these Wilson loops very far away from the core of the vortices. But really, what is really important there is that the length of the loop that you're considering should be much bigger than all physical length scales of the problem. Okay. And you will see that this is going to play an important role in here. In this particular. This is the size of the contour over which I'm computing the Wilson loop.
But the vortex string could be some finite loop.
So yeah, the vortex string. So if you were to look at a vortex loop, then it better be bigger than the size of all the microscopic length scales in the problem, so that you could compute a Wilson loop of size L that is, the size of which is bigger than all length scales of the problem.
Even if you have a small loop, you could still have a big Wilson loop.
Then you wouldn't get this. You could compute it, but you wouldn't get the effect that I was talking about, right? You have to sort of link the path of the vortex with the loop. If you computed something like this, you wouldn't get.
No, it will go through, but it will just go like very far away and come back.
Yeah, but it will then sense the physics that I don't want it to sense. So it will, if you are close to the core of the vortex, then you will sense the kind of physics that I don't want it to sense.
But this is important, right? Because you are saying the vortex loop.
Yes.
That you want needs to be also big.
Yes. Yes, it has to be bigger than these scales or these scales. It doesn't have to be bigger than, for example.
It is bigger than all physical length scales of the problem, but less than the size of the vortex loop, which is like it will view the vortex loop as a vortex string all the time.
Yeah.
I'm not quite interested in the size comparison between the loop and the vortex string and the Wilson loop.
Yes.
They are roughly kind of, you're saying the same, but they're big.
Right.
But smaller than the cutoff, right?
Yes. Yes.
So I could still be working with some.
That's right. Yeah.
Volume.
Yeah. Yes. That is definitely the case. So that's number one. And the second thing, so you will see which scales I really mean when I say that this has to be bigger than all physical length scales. So the second thing is I was using Wilson loop as an order parameter, but let me make it more specific what I mean by this order parameter. And so it's the Wilson loop around a vortex-like configuration. So this C1 is a path that goes around a vortex. But then I take a ratio of that Wilson loop with a path that does not go around the vortex. So C0 is a path that does not go around the vortex. Okay. So that's what I mean when I talk about the order parameters. So these two are kind of important, and I'll use them as I go on. So.
Are you still in the same model as yesterday?
I'm breaking the flavor permutation symmetry that I had in the abelian model. And so I'm just saying that these two things are going to be important, which I didn't clarify yesterday. One is that the length of the Wilson loop that I'm computing, that length should be bigger than the different physical length scales in the problem that I have, and you'll see which length scales I really mean here. And the other thing is that the order parameter is, I'm making it more specific what I meant when I wanted to compute. So this is a Wilson loop that goes around a vortex. This is the Wilson loop of same size that does not go around the vortex. So those are the two things that we need to keep in mind. And the third thing is, which I told everybody else, is that I'm actually not going to do a computation in this part of the talk. I'm just going to motivate what the results are. And I could describe how to do the calculation, but I'm not going to do it.
One question from last day. In case of particle-vortex duality, you can have vertices with a charge under topological U1.
Yes.
Now, here these vertices that you had earlier yesterday, are they charged under U1? Can you use that charge to distinguish between two sides?
So you're talking about the U1 electromagnetic field, right?
You had gauged model which has a U1.
Yes, yes.
Because it is gauged and
No, it is not. It is not charged in the sense that you're talking about. So you're talking about some kind of monopole configuration, right?
These vertices, just in case of particle-vortex duality, the vertices are very much similar to that, and they are charged under this symmetry. I am just asking, are these also charged under this symmetry?
So there is what is the symmetry in that case? So it's a topological.
You have field strength F mu nu.
Yes.
And define J mu
Yes.
as epsilon mu nu rho.
Right.
F nu rho.
Right.
This J mu is the current,
Right.
and under this.
Yeah. So that symmetry I have already broken, I think, by introducing the monopoles. So that symmetry is not. I don't think I have any
Right,
symmetry.
Right. So because monopoles break that, so that because this vertex presence of these vertices, if you add them in the action, that will break. So highly suspects that they are charged. They are all almost likely charged, right? You break that symmetry.
Mm-hmm.
If that symmetry is not broken, in case of particle-vortex.
So if it is broken, then why do you care about whether these are charged under that symmetry or not?
No,
He's
it might be
thinking the
broken in
vortex.
this background. It might be broken in this background.
Mm-hmm.
For example, the fact that this one-form symmetry in particle-vortex duality is not broken is
So first
a
of
statement of having photons.
Yes.
But when it is broken,
Yes.
this is broken because you have vertex excitations. So that way you
It's-
can use this symmetry.
No. It's not broken because of my vortex excitation. It's broken because of the monopoles, which is not this.
like objects in 3D.
Exactly. These are strings in that
But
sense.
you
It's
can
not
always
string.
state J mu for a two-index object. First, do you agree with this following fact that in case of particle-vortex duality, the vertices that you have, they are charged under this topological U1.
Under topological U1, you mean and define your topological U1 again?
So I have gauged model, gauge field is A mu, field strength is F mu nu, and the current that I am writing is J mu, is F mu nu rho.
Yeah.
Sorry, epsilon mu nu rho, F mu rho.
Right.
This is the topological U1.
Yeah.
And now, if this gauge field is Higgs, you can have vertex excitations.
Yes.
And so formally the operators which are creating these vertices, the question is, are these operators charged under this topological U1?
Yeah, but like she said, the topological U1 was not there in the theory because of condensation of monopoles.
Right.
Independent of anything vortices are. The monopoles, the condensated monopoles in the vacuum is breaking this topological U1. That's why the theory was confined.
Right. So you might not like to have this model with the confinement. Why was the confinement very much needed for the whole discussion? Let's say this is not embedded into an SU2.
If you don't have that, you will have a phase transition. I don't want that. That's why I
One
got
phase
it.
would have massless modes, the other phase would not.
That's what
Right.
Shiraz was explaining to me yesterday.
Yeah, so it's totally
Then there is
crucial for
nothing
her
to
that
prove.
that's
There
confined.
is-
Right.
So the other phase which was supposed to be massless if there was no confinement, this is supposed to be massive because of confinement.
Right.
And for that you will have monopole operators which condense and gives you the mass scale.
Yeah.
But if you are studying a model in which there is no confinement, if you are studying that model,
Okay, if we work at, it's completely orthogonal to what she's doing. Because she wants
Right.
to look at something where there was no phase transit,
Right.
right? Looked like there was.
See,
no obvious
Yeah.
reason.
She wants
Right.
to look at a case where there's Higgs and there's confinement, and then you want to know if there's a
To
distinction
interpret.
between them that's sharp or it's just a crossover.
Right.
Right.
And you
But
won't be able to
if you are
detect it
studying the model,
using
maybe
just
you don't
massless
have
modes.
the confinement. If
Huh?
you are studying that model,
If we're studying,
then you can try to find the same kind of vertices in the Higgs field,
yes.
and those vertices will presumably be charged under that.
I'm not, okay, we could discuss this, but
Yeah,
I'm
it's
not
not
even,
relevant.
I'm not even
Yeah,
sure it's
it's-
true.
Yeah.
Maybe after the talk, right? Because it's not, but it's, I'll just say one line. I don't even, it's not even clear to me this is true, because these vortices are vortices because, for a global symmetry,
Right.
not automatically connected with the gauge symmetry.
Right.
So you will say they are not charged.
They're not all necessarily charged. Now she showed in the Higgs phase they were charged to lower the energy.
Right.
But
Right.
roughly she showed that in the confined phase, she didn't expect that to be true.
Right. Right.
So it was not obvious that
In the Higgs phase, okay, it's not obvious, but I was asking.
Maybe we can discuss this later because it's not quite clear.
Okay.
By the way, this omega, the vortex strings that are being considered, can I think of them as some excited state of the theory?
Yeah.
Okay.
These are not really strings; they are particles, but yeah, they are excited strings. So I'll just write down the Lagrangian I had one
When
more
you say
time.
vacuum expectation value,
Mhm.
it's not point vacuum expectation value, but the vacuum expectation value in a state.
Yes, that's right.
Sign, yeah.
So this is the model that I had yesterday. So what I'm going to do is to give different masses to plus and minus fields. So let's say one of their mass is m plus, that's the mass of the plus field, and then the mass of the minus field is m minus. So what I'm going to do is define an average mass squared, and going to vary this average mass squared from positive to negative values. And there's going to be a parameter which I call delta, which is the ratio of the difference over the average mass squared, and I'm going to hold this fixed while I vary this parameter. And then ask the same question as to what happens to that order parameter. So what is interesting in this case is that you might wonder that when
n plus and n minus of masses of 5 plus of 10?
yes, yes.
You've not written that in the Lagrangian.
No, this is, I haven't written that.
Okay, fine.
Yeah.
Yeah.
So you might think that when I'm breaking the symmetry between plus and minus fields, you could have a regime where, let's say, phi 0 has condensed, phi 0 is always condensed. I'm going to keep phi 0 condensed throughout. But you might think that there might be a regime where phi plus is condensed, phi minus is not, or vice versa, and so on. But that actually doesn't happen because of this term. It makes sure that there is no such regime. So there are only two regimes. One is that phi plus, phi minus are both condensed. That's one. And the other is they are not condensed. Okay.
So this
Neither are
depends on
condensed.
the values of epsilon and
Any epsilon
It doesn't
is
matter.
ordering field on both phi plus and phi minus, right?
Right.
Any
It
two
forces.
of them are condensed, the third's got to get condensed.
It's like they have the same quantum numbers.
This is
Basically.
the ordering field, you don't need a symmetry between transition. Any two are condensed, the third's got to be condensed. So like
Okay. So now let me tell you what happens in the Higgs regime.
Which is any two are condensed, then the other one is condensed.
Yeah.
The past line seems to say more, right?
no, Higgs also. Phi plus is always condensed.
Phi 0 is
Phi
always
not
condensed.
Sorry, phi 0 is always condensed.
Yes.
So the first line is exactly what it is. One of phi plus and phi minus condenses, the other has to.
It's a tadpole for the curve.
Yeah.
Yes,
Yeah.
but past line is not stronger than that?
No.
No, because she's assuming phi naught is always
is what I'm keeping
phi
condensed
naught is
always.
always condensed.
Yeah.
Now,
Then
is
there
it the
can-
claim that phi plus and phi naught are always both condensed or none of them condensed?
Yes,
Yes,
that's what I've written.
Okay, so then
Either both of them.
That's
It is the
Yes.
same statement as saying if one of them
right,
condenses, the
right,
other.
right.
So,
But
yes,
but
go
now
ahead.
these two different vortex states
Right, right.
will no longer be degenerative.
They won't be.
Yes.
So, but it won't matter. So now I am in a regime where m average square minus of m average square is much bigger than e to the 4. So I am deep in the Higgs regime. So I'm going to now compute the Wilson loops around vortices. And I can just choose one of them. So let's say, phi plus is winding by e to the I theta, and phi minus is not winding. So these V minus and V plus are the VEFs of phi plus and phi minus. So they are not the same, and you can probably guess what is going to happen. So when I write down the effective potential now for the gauge field, I'm going to get okay. So now, because phi plus is not the same as V minus, alpha is not equals pi anymore. So it's not the Wilson loop that I was looking at, it's not quantized, okay? So that's what happens on the Higgs side. Now the question is what happens on the non-Higgs side? So this is where finally the physics of monopole and string breaking is going to be useful. And again, I'm not going to do the calculation. I'll just tell you the results and motivate why they are what they are.
So the departure from -1 of omega is proportional to delta.
Yeah, that's right.
So in the formulas for V plus square and V minus square, there's the delta hanging around all the
Yes,
time. And
yes.
you are also assuming, I presume, that the mass splitting
Is not
much
too
less
large.
than,
Right, right.
anyway.
Yes.
So where is this assumption?
Sorry?
Where is this assumption that the splitting is not very large?
So
This you could say for any value of delta, right? Or not?
So let's see. I think I could. So for example, if delta is bigger than 1,
But
I think I
not to the
still have-
extent that, I mean, I presume that when you have, this m average square is large and negative, both n plus square and n minus square have to be large and negative. That
Mhm.
much, of course, has to be ensured. It can't
I
be
better
that
have
n plus
that.
square is here and
Yeah,
n
yeah,
plus
yeah,
square is
yeah.
So that's what I was asking about this statement that both should condense, because m plus, the statement was the general kind.
Right.
So if I take m plus to be large positive,
So I
The
want
potential
this
still like
to
that.
be
Ah.
true.
I think what will happen is that classical analysis will no longer be valid.
Yeah.
Right.
Because you'll be, formally by classical analysis you'll get some condensate, but it'll be very small. And the effective coupling will go like 1 over that condensate.
Right.
So the classical analysis will no longer be valid.
then no. So let's say I take m plus to be very, very large.
Right.
Okay. So
Okay.
the potential is really steep up. There is
Mhm.
no Mexican hat type thing.
Right.
Then it's still condensed.
Yeah, phi plus will still have some wave, right? Because it's
Yeah.
there's a potential which is very steep,
Yeah.
but,
But
there's
it's
small
stilt.
time.
Yeah. It's
So
it's
still a
this.
small shift.
It goes to
Small is proportional to what?
The proportion 1 over n plus square,
1 over m plus.
right? Because
Sounds-
this is the
sounds
restoring force, and then there's a little push.
little push. So it's also proportional to epsilon, basically that term. Okay.
And then it won't be valid, because classical analysis is valid when waves are large, right? When waves are small.
Yeah.
Right. Okay. So now in the confining regime, the non-Higgs regime, m average square is much bigger than e to the 4, so it's positive, very, very positive. And so in that case, phi plus and phi minus don't have waves. Now, we are, sorry. So it's going to be useful if we work in the dual frame in this case, and I'll write down the Lagrangian in that case. So here is the action in terms of the dual photon field. So, yes. So what's happening here is that you can again integrate out phi plus and phi minus and write the action in terms of the dual photon field and the neutral field. So yesterday I showed you the same Lagrangian. I didn't write this term. This comes from the photon mass term. So that's cosine of sigma. This term was the Rayleigh scattering term, so phi naught square coupling to f square. This term, which was this anti-symmetric derivative between phi naught dagger and phi naught coupling to the f mu nu term, that was 0 yesterday because of the flavor permutation symmetry. Today it's not necessarily 0, right? It's going to be there. So,
I'm sorry, just, though you're not computing, you're saying you can reliably compute every
yes.
coefficient.
Right, yep, yeah.
Okay, and this is in some lattice model or something.
Exactly, so I'm not going to do the calculation, I'm just going to argue that this is how the result should be, okay?
If both m plus and m minus are large, then you can reliably do this.
Yeah.
So in that reason, this is reliably done.
Right, in that, yes.
Right, but just to get that e to the power minus s business, you need some cutoff.
Right, yeah,
So
yeah.
lattice model.
So,
This is what
Actually for a monopole, I think.
yes. Okay, so now I told you earlier that the length of the loop over which I want to compute this Wilson loop, I want it to be bigger than.
Just to be sure, so your sigma becomes an angle variable because you're on the lattice, or you're explicitly putting in the fact there is a compact U1?
Yeah, I'm putting in the fact that there is a compact U1.
It's compact U1 and it's on the lattice. Both are very important for us.
Yeah, I need this eventually for confinement to work.
I see.
Okay, so I want to compute these Wilson loops over the largest possible length scales in the problem.
Normalization of the potential, so that's small, isn't it?
That's small enough, I don't care about that. So what are the different length scales here? And so that's what I'm going to discuss now. So there is one length scale, which is the length scale set by the square root of the tension. And I'm not going to compute the tension, it's related to the fact that the photon has a mass, right? So I could call that the confinement scale. And then there is, so the corresponding length scale is given by 1 over the square root of the tension. And so this is basically capturing the fact that you had, if you had fundamental charged matter in here, and if you separated them, there would be a string tension between them. Now, on top of that, I also have a string breaking length scale here because I have phi plus and phi minus fields, okay? And that corresponds to basically the fact that when you're separating these charged excitations, the probes that you have, let's say, the corresponding energy, which is given by the tension times the distance, at some point that becomes of the order of the, let's say, whichever the lowest charge mass that you have. And so at that time, you will pop up these particles from vacuum, and that will give you screening. So this is the, let's say, string breaking length scale. So let me call it LBR. And so LBR is, say, M minus over the tension. And the hierarchy of that I want here is the following. I want 1 over square root of t to be much smaller than M minus over t. So the string breaking scale is bigger than the confinement scale. Now, when I compute the Wilson loops, I really want to be here, so bigger than all length scales in the problem. But I'll start from here and then go up to the bigger scales and show what happens. So,
I'm sorry, this effective action is valid in this rate. It doesn't
Yes.
have the string breaking physics.
it doesn't have the string breaking physics, right? So, okay, I'll just write this on this corner.
So it's valid at length scale, at energy scales low compared to string breaking.
Right. So, if I was looking at length scales smaller than the confinement scale, okay, I could forget the fact that the photon has a mass, okay, and pretend that it's free Maxwell theory coupled to those phi naughts, so on. And so now what you can do is to compute what the magnetic field inside the core of your vortex is by plugging in the ansatz. Phi naught goes as V e to the I theta. Okay. So if you computed that object, which is d mu phi naught dagger d mu phi naught minus d mu phi naught dagger d mu phi naught, plug it in here, you would see that the only component of this object that's non-zero is the r theta component. So let me call this object S mu nu.
So V is a function of R.
Sorry?
Phi naught is
This is the vev of the phi naught.
and it's a function of R in your vortex.
Yes, eventually, yeah, I should have written it like that. Maybe I'll write it as f of r e to the I theta. Okay. Or maybe I want to write it as v f of r e to the I theta. So f of r goes to 1 far away from the core of the vortex and is 0 in the core. So now, if you plug this ansatz in here, you can see that it's only r theta component that's non-zero, and it's given by v square f prime of r. This is derivative of f with respect to the radial coordinate, and then f of r over r. And
So f of r is something like e to the power minus mr, where m is the photon mass.
it is related
So
to
it
the.
should become 1 as okay, whatever, some.
I could write a form. It doesn't have to be like this, but this is a good enough form, I think. So this is a phi naught vortex. Maybe I should just write V. I meant this V, okay? So this is the coherence length that dimensionally wrong that was. So it's the coherence length that should appear here. So that decides over which distance this should fall off, okay?
The profile does not depend on the photon mass?
No, this is the phi naught vortex. It depends only
Oh,
on
I'm
the.
sorry.
Okay. Okay. So yeah, so I'm not keeping track of the dimension. It's just some function of v that you should make the dimensions work correctly. Okay, so this SR theta in the Lagrangian couples to FR theta. So that's the term in the. So this is, of course, dr a theta minus d theta ar. And so this term is going to be non-zero. Sorry, this term is going to be 0 for the problem that I'm interested in. You just hit d theta. Okay. So one thing you can do is take this term and integrate by parts. Okay. So when you integrate by parts this term, this d theta hitting this term is going to just give you 0. So there is no coupling between the radial gauge field and this object. But if you integrate it by parts this term, this dr will hit this and it will give you something non-zero. So as a result, you will get a coupling between a theta and there's going to be a current corresponding to this term. And that current is given by this. So anyway, so you can find what the current is, find what the magnetic field is, compute what the Wilson loop is, and the point is that you will not get this to be 1. Okay, it's going to be something different from 1. That's the first point. So for length scales that are smaller than 1 over square root of t. Okay, so now I'm going to go to length scales that lie that are bigger than 1 over square root of t and could also be bigger or smaller than the string breaking scale. So I'll just directly write down a form that's valid for length scale that are bigger than 1 over the square root of the tension.
So then this current creates a magnetic field in the.
There is a magnetic field in the thing, but the point is do you have any kind of excitation that can sense that magnetic field? That's the question I'm trying to answer here.
And the magnetic field is localized or goes all the way?
So it's actually localized. So it's
Because they get prime.
right, yeah.
So if you have magnetic field, then you will have a lot of.
Depends on what your probe is. So here I'm saying that it's okay to use, a fundamentally charged particle to sense this thing. But at some point, if you're looking at large enough loops, you will have string breaking. The only thing you're allowed is some meson-like structure. So you won't sense it. That's the punchline. That's what I'm going to get to eventually.
I understand. Because I could just compute the holonomy of a gauge field.
Yes.
If there is a magnetic field, I should get something there.
Depends on if you can. Sorry?
What is this thing about the probe?
So you will see that's related to the fact that whether you have a perimeter law or an area law associated with the Wilson loop that you're computing. Okay. Okay. So now I will look at length scales that are bigger than 1 over the square root of t. So that's bigger than the confinement scale. So if I am computing a Wilson loop around a path that does not go around a vortex, you know that the Wilson loop is going to go as this. So there's going to be an area law contribution, and there's going to be a perimeter law contribution. So this comes from string breaking, this comes from confinement. So the way this works is the following. So L is bigger than your string breaking length scale, then this term dominates and you get perimeter law. And if L is smaller than the string breaking scale, then this term dominates and you get the area law. Okay. Now, what happens when you compute this around a vortex? I'm going to just give you the answer instead of, again, computing what it is. So it turns out that the area law contribution carries the magnetic flux corresponding to this term. Okay? And there's going to be another contribution, which is the string breaking contribution, but this is not going to carry the information about the magnetic field. Okay. So again, this whole calculation, you can put your system on discrete space-time lattice, put a vortex in the space-time lattice, and compute this, and that's what you'll get.
So you're saying the second term is unaffected?
Second term is unaffected. Yeah. This is simply because, you know, again, you just have meson-like excitations, and they can't sense. Or rather, if you're dragging a particle around your vortex, you would pop out a minus particle, and that would sort of screen the probe that you were taking around. So that's what this is.
Everything decays exponentially, so it just doesn't sense what's happening.
Yes, yes, exactly. So what happens to the ratio that I was computing? So you take the ratio of this one with that one, and I'm just going to write what the answer is. It's given by 1 up plus corrections that are exponentially suppressed in the size of the loop. Okay. So it's basically because of confinement and string breaking. This order parameter that I was computing is 1 up to corrections that go in the size of the loop. So if you took L to infinity, which is what I eventually want to do, these go away. So there is only one kind of topological information in this thing that I'm computing, and it's this 1, which does not depend on the size of the loop. Okay. So this is now really where confinement, the physics of confinement, played a role. So the diagram that I had drawn yesterday between the holonomies or the Wilson loops on the two sides gets modified a little bit. Okay.
You had this action at least which was taking care of these monopoles. So you can compute the first term carefully with that analytically.
Mm-hmm.
The first contribution you
Right.
can calculate, right?
You can compute the second also. You have to put it on a lattice and do an appropriate expansion. To put in all plaquettes and so on,
Right,
and then do a
other expansion, but
Right.
on this continuum side you can do the first one, I guess. The first term you
Mhm.
can
Yes.
compute.
right.
So that, okay. And your point was that if you take the loops large enough, then if the size of the loop is large enough, then the final conclusion was that it was still 1.
It's still 1 because these are the terms that are going to dominate. Okay, and they are not going to sense.
They do not at all see the confinement.
They do not see the magnetic field.
Right.
Right.
That was the point. If it is large
Yes.
enough, it does not see. Sorry.
No worries. So this is the diagram that I was drawing yesterday. So I had my order parameter.
Sorry, why did
Pro-
you
So I was plotting this with respect to m charge square over e to the 4. Now I'm going to do m average square over e to the 4. So this is positive, that's negative. So on the negative side, things were quantized at -1. On the positive side, the holonomy was quantized at 1 when I had the symmetry. Now on the Higgs side, it's not -1 anymore. It's something that's not -1. So but on the confining side, it's still strictly 1. okay? So again, that means that there has to be a phase transition. If you want to approach, for example, if you're approaching from this side, at some point you have to move away from 1 to get to -1 on this side, okay?
But we do this continuously.
No, so for example, think about the derivative of this object, right? So it's 0, strictly 0 on this side.
So why 0? Strictly, it's some infinite thing, right? Some mass infinite thing.
No,
It just derivative approaches 0.
it's 1 plus corrections that are suppressed exponentially in the length. So I just want to keep this 1.
Why?
Okay?
Why don't you want to keep the line?
Because this is not, so this information is not topological, okay?
But it
This is not-
depends on length, right?
That's fine. You would want to keep, you would only want to keep the information that survives in the L going to infinity limit.
Why?
Because this is length dependent, right? That's,
No, but why are you interested in taking L going to infinity?
oh,
This is some dynamical state in the theory, right?
no.
What you are doing, this vortex change, is some dynamical
No, I
state
don't-
in the theory.
Yes.
And,
It's not, right now I'm treating it as a probe, okay?
so this goes back, I want to go back to my question in the last lecture. Are you including, so presumably at the end of the day, what one would want to show as a diagnostic of phase transition is whether the free energy is analytic
Yes,
in this parameter or not.
yes,
Free energy computed in some infinite volume,
right,
right?
yes.
So there, are you going to allow for infinite length?
So this is a different, so this is the point. This is to be used as a probe. It tells you that there is a phase transition. It does not necessarily mean that you have to use this information to compute the phase transition. It detects the phase transition, okay? And this is, so where else is this useful? There are other contexts where this is useful and where condensed matter physics use this kind of probe all the time, which is when you have topological phase transition, okay? You either look at, you look at holonomies on contours of size L, or the other thing you can do is to put your system on a torus, okay, and compute holonomies again on different cycles. And there, the information that you get, the only part of the information there you care about is what stays finite when you take the size of the system to infinite, okay? So this is really that physics.
No, but you're taking L also to infinity.
L is the only thing that I will take to infinity.
Well, you're taking the system size to infinity, so that I agree with. But
This-
why is L being taken to infinity?
So the only, so
I mean, in other words, if you are including that infinite energy
I don't,
configuration,
yes.
then already
I'm not going to, no, I'm not going to use this configuration to compute my free energy. This is going to tell you that there is a phase transition. When this is something that's detecting the fact that there's a phase transition.
This is externally specified by the.
No, but you cannot do that, right? Because it's some state. I mean, in order to use, we want to compute free energy, right? At the end, right? The
This is
argument
not
has to
good.
be
This
about the
yeah. But I am not going to use this
Okay.
as an argument for non-analyticity. Their non-analyticity is already there. This is detecting that there is a non-analyticity. Okay.
So I don't quite see why there should be a non-analyticity in the free energy in some infinite body.
But this L is not the vortex loop size.
It is.
No,
It's-
this L
it's
is
n-
it's the size of the Wilson loop, no?
It's the size of the
But
Wilson
we
loop.
just saw right in the earlier discussion that you need the vortex loop to be also large. Don't you?
No, it's
I-
not coming into.
That's fine, but okay.
You just said that right in the last.
Yes.
You want the vortex string loop also to be very large.
Right. So I'm not sure how you can use this information directly to be fed into your free energy computation. I could imagine how that would happen, okay? But I don't think I can right now prove to you why it is true that the information that survives in the L going to infinity limit is the only thing that's important. But there is good enough evidence that this is good order parameters. There is an example where this can be used as a good order parameter, and that, for example, works exactly how, for example, how superconductors work. Okay, so in ordinary superconductors, when you have Cooper pairing, for example, okay, so your U1 gauge theory gets broken down to Z2. So what is the Z2 there? The Z2 there is the fact that you have two degenerate states. Okay, they corresponds to, one of them is the uniform state with no vortex in it, no flux tube in it. Okay, that has a holonomy of 1, and the other one is the superconducting flux tube where there's a magnetic field inside it, and the corresponding holonomy is -1. So that's the Z2 of the Z2 gauge theory when you break U1 to Z2. Okay, so and in that case, when you compute the holonomy of the state which has your flux tube, you actually have to take the loop size of the loop to infinity. Okay, it's the corresponding holonomy is not -1 strictly. Strictly -1. It's -1 up to corrections that are suppressed in the size of your loop. Okay.
Can I just confirm this? I'm maybe understanding wrong. But so far you have shown that even if you have confinement, you can make your loop big enough so that you can forget about its effect.
Yes.
This is you have shown.
Mm-hmm.
Mechanism of confinement so far did not play any significant role because you can make your loop big enough.
Yes. No, but yeah, you could say that. So you need confinement plus string breaking to work, right?
So
Otherwise, it wouldn't work.
Using string breaking, like it's big enough,
Right.
then you can ignore it.
Right.
This was the
Right.
point,
Right. Right. Yes.
Mm-hmm.
But if you didn't have confinement in the first place, then it wouldn't work, right? Then I would have non-zero magnetic field, and I would be able to sense it, right? Right.
So I have a related question to it. So how do I connect these two things? Like first you have some non-analyticity in the behavior of this Wilson loop, and the other thing is possible phase transition which would be characterized by non-analyticity in the free energy.
Yes.
But why should this imply that?
This is what I'm saying is that there is good enough evidence that this implies that.
Why?
Okay? Why is a different question. So for example, I can ask you the following question. When you have, let's say, Landau paradigm, okay, and you go from a region where some symmetries are broken and the symmetry is not broken, okay, can you prove it like, how do you take that information to show that there is a phase transition? You always, personally, I see that whenever that happens, there is a phase transition. Okay, I can relate the fact that the symmetry is broken on one side and is not broken on the other side. Always there's a one-to-one map with phase transition. That's how I understand it. Okay, and it turns out that in all examples that people have looked at before, this difference that you can detect using topological order parameters, that if there's a sharp jump in that, that corresponds to a phase transition. Okay, so that is how I understand it. Now, I would, if you were asking me that question, I should reflect back that question to you, because this is something that is regularly used in condensed matter physics.
That is true,
Right.
but I still wonder how it is.
So I would ask that question to you. Okay, I have looked in the literature, and I haven't found a single proof where this was shown to be directly giving rise to a phase transition. It's always the case that whenever there's a phase transition, or whenever this is true, you find that there's a corresponding phase transition. Okay, so they go hand in hand.
So what's the statement that's not true?
So Abhijit wants to understand as to how I can use this information directly. So, I have these loops, I get something topological that doesn't depend on the size of the loop, plus corrections that are exponentially suppressed in the size of the loop. How do I take that information and then conclude from there that there is a phase transition? Whenever, if the topological part of it that doesn't depend on the size of the loop, if that jumps, okay, how do I use that information?
I mean, at the end, the bottom of the objection is basically that this is being done to an excited state. This is not detecting properly the ground state. So, in excited states, you could usually have tunneling, right? And which will be like the infinite volume effects, which are the things that are giving rise to phase transitions. So you could just simply be in some superposed state all the time. And how is one getting rid of that superposition? I mean, in the taking L going to infinity limit, what is being done, I think, is that you are now saying that superposition kind of thing costs infinite energy. There is no tunneling. Okay, but if that is so, then this would then be a statement about a path integral where a topological winding of phi naught field has been imposed to begin with.
So you are giving an argument as to why there could be no phase transition, or this couldn't tell you about a phase transition. I'm saying that I don't want to go to that. I don't want to argue by that through that way. I'm just telling you that there is a difference on the two sides, and I have enough proof to show you. For example, in certain cases where, well, I didn't show you that, there is a weakly coupled region where the change in the solenomy actually does coincide with a point where there is a phase transition.
Yeah,
okay?
I understand, but I think there are two questions. So when you do path integral, okay, so when you want to compute free energy, you do path integral, and then in order to do a path integral, you have to specify some boundary conditions.
Yes.
Let's say you are in a system whose size is going to infinity, so you have to specify some boundary condition.
Yes.
So you could ask two things. One is what happens to the free energy
Yes.
associated to the boundary condition where phi naught has no winding.
Yes.
Okay, and what happens to the free energy with the boundary condition where phi naught has winding 1. I think it's the latter one for which I think these arguments would be valid for the latter question.
Okay.
That the free energy of the latter question, where you do have a path integral where a specific boundary particular winding 1 has been specified.
Right.
Then I could understand perhaps that that particular free energy will be non-analytic, let's say,
Right.
in this limit,
Right.
in this thing,
Right.
as a function of m. But for the first question, where you are doing a path integral where zero winding has been specified at infinity, and then you are doing the computing the free energy.
Right.
I don't quite see why that free energy would be non-analytic, because that free energy will not have this infinitely long.
Yeah, so I'm
coordinates.
saying that you don't have to use this as an input.
But what is your statement? Is it that the first free energy is
Non-analytic.
non-analytic, or
Yes,
the second free
yes. It's my statement is that the first free energy is non-analytic, and this is just detecting that. You don't have to use this in your path integral. Okay. So what is it really detecting? It's really detecting the fact that in one phase you have a macroscopic quantum wave function. So the fact that this is quantized, or this is different from one side, is really a result of that thing. Okay. So that is a property of the ground state, except for the fact that I can't detect it in the ground state. Okay. So when I look at it using a probe, which has what you call as an infinite energy probe, what is that probe still has coherence. The corresponding field configuration is still a macroscopic field configuration. Okay, where you have coherence, right? So that's sort of the property of the ground state that is reflected in the kind of excitation that I'm looking at. Okay.
Could I say one positive thing? It's in your winding number 1 phase, I think she will get she will have an argument for the free energy having a jump in an extensive way, because in that winding number 1 phase, the Wilson loops that are detecting this are arbitrarily large.
Yes.
And so now it sounds sort of unreasonable that an extensive quantity could have a jump or not because of one thing. Because that should be local.
It's topological though.
The probe is topological,
Yeah.
but if you are willing to agree that probe indicates that there is a non-analyticity of the free energy proportional to volume in the winding number 1 phase. If you give me that, then I think it's unreasonable to say that it doesn't happen in the other phase. If you say that in this winding number 1 phase, there's a volume times function of temperature that has non-analyticity, then putting one thing there, how can that change the volume part? If you agree with the first statement, I'm not sure you'll agree with that.
I mean, energy of such a thing
is infinite.
is proportional to volume, presumably, right? Or not?
No, it'll be a length type.
Length type energy.
So
Yes.
it doesn't sound reasonable to far away.
But non-analyticity could be just in length, right? Doesn't necessarily have to be in volume. Why does it have to be volume? You could have absorbing temperature factors.
Well, in the case of, let's say, maybe we could, but anyway, in the case of a say we just have the usual order parameter for confinement. A very large Wilson loop is either area law or perimeter law, and we take that as good enough indication that there is a volume temp phase transition. So it seems to me that it's reasonable to say that in the winding number 1 phase, for the same reason, there's a volume temp phase transition. Because it comes to something very large. I'm not sure of anything else. But if you buy that, if you give me that, what she's saying sounds close. But then it has to be something local.
Well, I would say in this case then it's a length time.
Okay.
But it's probably irrespective of what is happening in the ground state, it's still probably a very important statement that if you create a boundary condition such that there is a vortex of this type, then this is clearly behaving differently.
That I think I would agree.
And there is a phase transition.
Yeah. And I'd say one more thing.
Yes.
The way you word it, you say you have a vortex.
Mm-hmm.
I think both Abhijit and I would be just more comfortable to saying I do a path integral with some specified path. You know, some cleanly specified.
The whole issue is the subtlety is the fact that you detect the phase transition by a property of excitation.
Yes.
Yeah.
Yes. But I'm just saying that this
But
is.
we know other examples of that, but no, as you say, no. I mean, there are other examples, I guess, where it is true that the best way to detect some transition is abrupt change in the property of an excited state, but that doesn't prove that there has to be a phase transition. The other examples I know there is a phase transition, but computationally the easiest way to detect it is to look at a change in the
Right. So I'm making a conjecture here that this is going to tell you about a new way of detecting a phase transition. It doesn't fall into the.
It sounds very plausible to me, frankly. But let me say one thing. Suppose instead of you want this to be a dynamical vortex. You wanted to solve the equations of motion.
Okay.
I don't see where that was needed in your argument. Suppose you specify a new disorder line operator in your
Yeah, that's what I was going to say.
Yeah.
Could you not specify, could you not get to the same thing by looking at the correlator of, exactly.
This is what I mean.
Exactly, in the ground state. Because
That's
you
what I
create the
okay,
vortex
yes.
and then.
Right.
Yeah, you could probably
Right.
do that.
So you could formulate it like that. You have to create, you have to act as an operator on the ground state that creates this excited state.
And
But
you
create
Yeah,
that
you
on
could
the
do.
both could.
No, so I'm thinking of the Hamiltonian, and this is a point excitation in the Hamiltonian. It's a particle-like excitation in the Hamiltonian.
Yeah.
2 plus 1D, it's a vortex.
Say we do this
So the length
with
is the
two
red
different
line.
line operators and make that both large.
Siraj, I think for him it might be easier to say, look, this is a two-dimensional Hamiltonian, right? I'm applying a local operator at a point which creates a vortex. That's cleaner,
Right.
right?
I
So
doubt
then there's
that's
no
clear,
objection.
but okay. But okay.
Right.
Your time is just zero temperature, I don't care.
No, that is an infinite energy particle.
No.
No.
It's got finite core energy. We just established that. That's the whole point. One vortex excitations are perfectly okay excitations in this theory, right? Well, you have to put another one far away. You have to put another one far away. You have to
Yeah.
put another one far away.
Diverging.
Right. But so what is the?
So, okay,
So this
you
is.
always create a pair so that there's no
finite.
network.
Do this.
Okay, but I don't want to think space time, right?
So this is like any other particle. For example, your charged particles have logarithmic energy,
Plus
right?
vortex here and a minus vortex there.
And it's just log of the distance between them.
Bus.
Can you just say one more thing? Toft had these standard things, right?
Right.
A Wilson loop interlinking with a Toft loop.
Yes.
This sounds very much like what you're doing.
Mm-hmm. Yes.
Why don't you just do it that way?
Well, I'm not in 4 dimensions, so I'm a little bit.
L with
Yeah.
infinity is crucial, right, for that form to be constant.
Okay, I agree.
Okay, yeah.
That is what about
But that is.
I create a vortex separated by a distance that's large compared to the screening length, so that
Yeah.
there is a magnetic field. Of
Exactly. That's my point. So long as you're bigger than the screening length, you should be okay.
You just create two vortices, 1 plus 1 minus, so that there's no net winding, there's no divergence. You just keep them far enough apart that the screening properties of each vortex are not affected. Whatever magnetic field is contained in the vortex has died down before the next.
Right.
vortex
That
arrives. Then this
that
is a
really
key
matters.
situation. And then she has a statement to make about correlators of such operators.
But the fact that you're using fact that the derivative is zero.
right.
But derivative is zero.
I don't think that matters. I don't think that matters. The thing that really is going to matter is that this L is bigger than the screening length in the problem. Okay.
Yes,
So it's 1 up to corrections that are exponentially suppressed in some length scales that I don't care. As long as that length scale is small.
But if we establish that the excited state properties change.
Right.
Now to make that a statement about ground state, presumably you're going to have an argument of this type.
So any analytic function, you can make it very close to constant in a big region.
Sure.
Right? So in that big region, you can make it to be 1, but it could still
Yeah,
be,
yeah.
like a smooth way and connect to that. Right?
Yeah, it could. Yes. So if you take into account that part of the thing, that yes, it would. But then I want to throw out the information.
It has to happen.
I want to throw out that information. I want to throw out what goes to what is not finite in the limit of the
end
length.
point is, yeah, so you're saying it could just smoothly go, but I thought you already
The
argued.
argument I thought was that because that line there is 1, just 1,
Yeah,
nothing
yeah,
else.
yeah, yeah.
But that
Yes.
requires L going to infinity.
Correct.
So that's nothing 1,
L is the
then the
spatial
derivative
L.
is just 0. So
L is the L by L box of the Hamilton.
This is true even so whether so there are 2 points here. Point is whether you want to throw away that information, and on top of that whether you want to use that fact that you are throwing away that part of the information is going to affect your path integral or not. The first point is when you say whether it's okay to throw out that term, there is nothing specific about this thing being having a logarithmically divergent energy. Okay, it is true for all kinds of systems that you look at. It's true for even for ordinary superconductors, for example. Okay, you will have to throw out corrections that are exponentially suppressed that go as exponential of minus L times the whatever length scales in the problem. Okay, so even in that case, you throw out that piece of the information. Now you want to argue whether it's okay to throw it out or not because I have logarithmically divergent energies. I would say that it is still okay to throw it out because so long as I'm not doing anything to the magnetic field that's contained inside the vortex, so long my length scales are bigger than that length scale, I don't have to worry about it.
Yeah,
That
that's what
part.
I'm saying. If the statement is about length scales, as I said, any analytic function you can make it to be constant in a very large area. You want really a strict statement to make such a kind of thing. So if you do this kind of approximation, then this line will stretch for a long time to be 1, and then it could still smoothly go to that.
So when you're saying it will stretch, it's stretch for a long time, are you saying that it's going to be strictly 1 or not?
No, it's not. Because
So
if it were strictly 1, then I agree. If something
So it is strictly 1 up to this correction, which I'm saying I am willing to throw away. Okay, so that's my definition.
But could I, what is wrong with the infinite L limit of this divided by this?
So what is your L analysis?
Just could I write something?
Yeah.
What is your L?
The size of both loops.
L is not going to be your size of a box.
No.
No, box is infinity. Box is infinity to start with. Let's say. Suppose I do limit L goes to infinity. L scaling. I scale the whole thing. This quantity. Isn't this a clean of the time? Link or don't link? Take the linked loops divided by don't link loops. In one case they're 1,
Yeah.
in the other case they're something else.
Right. And they are not infinite energy
These are
configurations.
finite. The limit, and any L is finite.
Yeah, you are right. Yes, I could do that. Yeah.
Abhijit's not.
It's an inherently a statement about infinite L, right? Phase transitions should be some infinite.
No. Yeah.
The infinite L that you are talking about for the phase transition
Is a volume.
It's a volume.
But this is
a
getting
different-
comparable to that, right? I mean, I'm not.
It could be.
No, so
Not
you have to
necessarily.
make a distinction between the size over which you measure and the size of the box. The size
Right.
Of
Make
the
a
box.
different scale.
Yeah.
Yeah, first take V to infinity, that's already infinite.
Well, okay.
I mean, just we're working on R3. And then take this observer.
No, but Shiraz, in this, where does the limit eventually you are going towards the m average square equal to 0 region, because you want to you basically that's
Yeah. What I want to do is fix M average square, where I can reliably do one calculation and then show that this thing.
No, but then the point is that still the possibility remains that
No, in that
from 1 to minus 1 it goes
no.
continuously.
So in that limit, you should be able to throw away the at least.
Because we're taking L to infinity. Keep M average fixed.
Sorry. Yeah.
But if you need to finish, we can continue the talk.
Okay. So it's 12:47. So
sorry
regarding
for interrupting.
no worries, this is fine. I have some material, but I don't know if I want to do them or should I end it? Is what I'm wondering. So I could end it here, so that's fine.
Do you have any argument for quantum corrections? So far everything was classical.
Right.
Like if m square goes to, you said that you had some symmetry argument or something?
No, that was for yesterday. Right.
Today you have, so it's only reliable computation at classical, like m square going to infinity limit and then all this.
Right. Yes. And on this side, quantum corrections are not going to move it away from 1. Is what my belief is.
So what was the argument for that? Why not? I mean,
You told us, I have the same sort of question. You told us yesterday that you do the classical analysis. And
that was yesterday when I had a symmetry argument to tell you, why things were quantized on the two sides. And here, on this side, it's not even quantized classically, right? And on this side, it's 1 because of confinement and string breaking. This side, I don't expect quantum corrections to change anything. So if you want,
you're saying there is where you have control, not here.
Right.
There you have control because of what? At least what helped you to have control that side?
So in there again, I am deep in the m average square much bigger than e to the 4 limit.
But if you make that m average square small enough, then you don't have control.
No, I don't have control. Yeah.
But I think she's saying that the 1 by m average square expansion was control.
Right.
Because her effective action that led to these conclusions, led to half of these conclusions, were in 1 over m average square expansion.
Mm-hmm.
And she did an operator analysis. She asked what operators could affect this.
Right.
And I think
Yes.
no operator.
There is that's right. There is no operator that you can write down.
Even if you have higher order terms.
Right. I don't think that they could affect this.
I think that's mostly the side.
Yeah.
If there exists one, yes.
Right. Yep. Okay.
Maybe we can clap. Any questions?
So just to understand what's going on. So there is one dimensionless parameter here, which is m square by e to the power 4.
Right.
And I guess what Shiraz's interlinked thing is doing is that it's inventing another dimensionless parameter, which is m square l square. I mean m square l square. So that if I stay sufficiently away from the origin in that axis, I can go as close to the origin here. I mean, just to say that there is another axis coming out.
Right.
That's ml.
Yes.
Okay.
Yes.
And I can choose that, keep that ml to be very large.
Mm-hmm.
And when I do that, then I'm allowed to come here all the way up to this
close.
dimensionless parameter to be equal to 0.
Mm-hmm.
Okay. So I stay in that plane. Okay. And then there I find that I'm just going like this. Yeah. Is that?
The one thing I would add is I don't think we know where this will happen.
Right.
Because you can reliably calculate far
on
out
this
here,
side. Yes.
Yeah.
but in this region.
Yeah.
Right.
So somewhere this will happen.
Some other way, yeah.
Whether 0
That's right.
or 1 no.
Okay. So there's of course, this is not then allowed to go to infinity really because of the size of the
This
box.
is allowed to go to infinity, but your other parameter is not. We're allowing this to go to infinity at large values of m squared by e to the 4.
Mm-hmm.
Oh yeah, for the calculation, because
Okay.
for the
Okay.
calculation I need that
Yes.
thing
Right,
large
right, right.
anyway also.
Yes.
Yeah.
Okay, so then the point does remain still, even with that technology, that whether you could have a smooth transition from one to from here to here in the region where you can't compute, like in here.
Yeah, this I think is related to Interneal's question, because he was asking, suppose we know
Yeah,
that,
yeah. Without that symmetry.
suppose we know that this is really flat.
Yeah.
Then that establishes that there's in a neighborhood we know that this is flat. Then it establishes there has to be non-analyticity somewhere.
Right.
So Interneal was asking, how reliably do you know in this axis? Let's say we all give her this axis.
Right.
How reliably do you know on this axis if you go away from infinity? Is it genuinely flat and there's no small correction? I also think that's a very important question.
Yeah. So to that, I would say it's got to be 1 plus corrections that have to be smaller than what I have already written down.
No, but my
Because-
idea is infinity. Let's
Right.
say-
Then it has to be 0.
that
Because otherwise, that calculation that I have done makes no sense. If quantum corrections could actually overrun this correction that I have written down,
Sure,
right?
that's one thing. The other thing is that for even to arrive at this result,
Yes.
you do need m square by e to the power 4 to be
Not infinite.
large.
It has to be large, but it doesn't have to be infinite.
It doesn't have to be infinity, but there will be some, some kind of, you do some expansion there.
Yes.
And there will be some radius of convergence of that.
Yes.
And at some stage in the value, there will be some value of m square by e to the power 4.
Yes.
Where you can't push your.
Yeah, so it'll be somewhere here, let's say, okay? Here,
Good.
these corrections, whatever quantum corrections you get, have to be smaller than what I have already written down.
Good. So that we take care of by going, very large in the ML.
Yes, in the L, yeah, going into
I think
larger.
she's saying that as long as we know that there are these string breaking effects,
Right,
this is just very robust, right?
yes, that's right,
Because this is just a fact of string breaking.
right,
So,
right,
and that is expected to hold true in a
yes,
region.
yes. And I would also like to point out the fact that even outside the question of whether there's a phase transition or not, we believe that there's a phase transition. We need to prove it. So there are certain examples where I showed that this does coincide with phase transition. Okay. Now what one could do is where I don't have control, someone could do a lattice calculation and see if there is a phase transition or not. My claim is that there will be. Okay. But beyond that point, I would say that there was no other parameter that people could write before this that could tell that one is different from the other. This is the first time I'm writing down something that can tell the difference between Higgs and confinement. Okay, so yeah.
And if you can word it in some language like this, then it's as good or bad as the question of whether a Wilson loop is area law or parameter law.
Yeah.
That's not directly a statement about the free energies. It's sort of clear that it implies.
Well, so I think there's perimeter law on both sides for very large loops because there is matter content on both sides, right?
No, I was using it as in a theory without fundamentals.
Oh, okay.
It was widely believed that if the area, if you can show it's area law on one side, and
Oh,
parameter
yeah,
law on
okay.
the other side,
Yes,
that
yes.
implies a phase transition in the free energy band.
Right,
Yes, this is not a statement about the free energy.
right.
But for the standard reasons, it's believed that it's.
Yeah,
I think
yeah, I
this
would
is
say that.
Sounds to me like similar.
So, yeah.
Yeah, you can always bring in heavy quarks, fundamental quarks as probes, which has nothing to do with the dynamics of the theory.
Right, right.
Like for the polygon loop as well.
Right.
It's nothing.
Exactly.
In
Exactly.
the
So we
theory.
do this all the time.
We do this all the
So
time.
why are we holding her up to a higher standard?
Yeah.
I think not. I think his only worry was if this probe is also as expensive as the it scales in the same way
Volume.
as exactly.
But
So-
suppose you word it like this.
Otherwise
So
she's fine.
when you are in 2 plus 1D, the interaction of these vortices go as log, which is the same as the interaction of particles. Okay, so their interactions are not very different in that sense. Okay, so putting a particle would cost like normal positive, negative charged particle would cost you the same amount of energy as a vortex would.
Yeah, that she doesn't scan about. That's any extensive quantity. No extensive quantity can depend on one or two extra particles.
Yeah, because this will still go up as log L and it's
different from
going to lose. Yeah.
Right.
Do you think that if instead of these muons, if you have non-abelian groups, then you would have similar phenomenon that interesting for studies?
Yeah,
Because earlier you started with SU and with M fundamentals.
right. Yes. I
In
would think
2
so.
plus 1 dimensions.
Sorry?
In 2 plus 1 dimension, would you think that
Yeah, I would think that would be interesting, but this phenomena would also work in 3 plus 1 dimensions for SU and gauge
yeah,
theory.
because then in larger group you might have more control than just Higgs classical.
Right, right. In large N, yes.
Might
Yes.
have some other limit in which you have more control, maybe some quantum corrections.
You might have that, or you could. The difficult thing with SUN theory would be that in 2 plus 1, I'm not sure. In 3 plus 1, I know that I really don't have control on the confining side. So you would have to find some dual of that theory to be able to compute.
You have fundamental matter, but in number of them.
Right.
You don't have adjoint matter, you have fundamental.
That's fine.
So that
But
might
still, when the fundamental matter is heavy, let's say,
be heavy.
positive mass squared, right? It's this, right? So I would think that the theory is in general strongly coupled, right? And unless you have a dual theory, you wouldn't be able to do a calculation, right? Some, I don't know, some ADS CFT thing you will have to do.